Hi, I'm Marco from JetBrains, and my talk is called Why You Don't Need to Worry About Scaling Your Java Web App. What a short title. Now, how did this talk come about? The thing is, I don't know about you, but it happened to me in the past. You built a new project, and then shortly before release, go live, a business person comes in and asks you, hey, it's all nice and dandy, but are we gonna scale? What happens if we're gonna be the next Amazon tomorrow? What happens if we get like thousands of users, 10,000s of users? Will we be able to handle it? And it was always like, well, I don't know. I hope so, kind of. And also, I do a fair amount of stuff on AWS. And if you're not used to AWS, just a quick thingy, you have these, Amazon EC2 allows you to spin up machines in the cloud. You have different instance types. Instance types means different amounts of memory, CPU, I/O, and whatnot. And when you look at the website, you have this general purpose section here with these different instance types: M7A, M7G, Mac, M6G, M6I, M4, A1, whatever, and then you click the next section, computer optimized, it goes to C7, C6, and you have all these hundreds of instance types, and I always wondered, well, what type of instance would I actually use? And even if I'm using like a container-based deployment on Docker, how many CPUs do I need? How much memory do I need? Where does my application, waste its resources so I can actually scale properly and not just mumble, yeah, Kubernetes auto-scaling, whatever, and it's just gonna work. I wanted to get some cold, hard facts, and this is essentially what this talk is about. So we have 3 parts in this talk, and the first one is we're gonna spend a tiny amount of time on some simple load testing. It's all gonna be done live. There's no slides, almost no slides. And we need to do some load testing for a simple web app because I can't just tell you, you need a C6I instance for your web application. We need to get some numbers. Getting some numbers leads us to the second part of the presentation, which means we need to collect a fair amount of data, generate the data, analyze the data, and I'm going to tell you exactly what we're going to be looking at in terms of performance data, CPU, memory, and whatnot in a second. And the third part is we're going to look at some general practical considerations, implications, day-to-day real-life challenges when it comes to scaling your stuff. All right, so that means I'm going to show you a bit of my lovely handwriting. That's the scenario we're going to be looking at, meaning we have a Spring Boot application. It doesn't really matter. It could have been any other Java application. It's a Spring Boot 3 application, and it's not a microservice landscape. We're not immediately going to have 20,000 machines booting up. I want to keep things simple, show you the concepts, and later on we can apply them to the whole bigger picture. The Spring Boot application only has one endpoint. I'm going to show you the code in a second, which returns JSON. And it's based on Jetty, the web server, not on Tomcat. The reason being that the Jetty maintainers or creators actually help me with a fair amount of knowledge, because they have quite huge Jetty installations. They do consultings, and I wanted to just get their experience on some things. So I'm using the Jetty web server here. Right, so Spring Boot server. And then most of you will have done some load testing in the past. So what we're going to do is we're going to be good citizens, meaning we're going to have our server. We're not going to do what lazy devs do the load testing on our dev machine. Instead, I'm going to have 1, 2, 3, 4 loaders, which you see here, these L boxes on the left. And they will just hit our server with requests per second. 1,000 requests per second, 10,000, 100,000, whatever. Why do we have 4 loaders? Because it's actually relatively easy for loaders to get overloaded themselves, generating the load. And we want to make sure it doesn't happen. So we want to hit the server with the full throughput, so to speak. And there's something else which is debatable in load testing circles, but our loaders actually, they just generate the load. So they just shoot, their responsibility is every second generate 10,000 requests, for example. but we do not record the response times these loaders get. Instead, we have a tiny probe, which is another machine, isolated. It simulates a user, which just does 1-2 requests per second, and browses, the server, or, calls the endpoint. And the probe records all the latencies and response times. And we want to find out, hey, how do the response times for the probe change here, hitting the endpoint, while we crank up the load here on the left side? That is the scenario we're going to be looking at. And that's it for the load testing part, so to speak. I'm just going to quickly show you the code for our Spring Boot server, because it's actually rather simple. If you're not using Spring Boot, don't worry. It's just one class. It's a text controller. It only has one method called textRate. It returns a new Java object, new textRate object, which always has the name German VAT, Umsatzsteuer, and with a random number. I just wanted to simulate some load on the, some work on the server, and then that object gets converted to JSON, and that's literally it. That's all the server does at the moment. And the loaders and the probe, they all hit this very endpoint, and we just crank up the load and see what's going to happen. That's the server. What I also have is I have a tiny application which essentially is just one Java class. And you can see it just has, 1 or 2 lines of code. And we can talk about, if you have questions about the codes, please hit me up after the presentation. But essentially what it does, what this one Java class does is, I'm not using JMeter. I'm not using Gatling, which you can very well use. Instead, I'm using, again, the Jetty maintainers have written their own load testing library. And it's just a Java library you can, put into your project. And by the way, let me just quickly run this, because I wanted to run the load test live, and it's going to take some time for them to execute. So I'm just going to quickly run this class while we're waiting, right? And what this class does is it boots up the server in AWS. It has these loaders. It has the probe you just saw, and it runs 4 times. So there's 4 load testing scenarios. And in the first run, every loader shoots 250 requests per second against the server. So in total, we have 4 loaders. It's 1,000 requests per second. The second run is going to be 5,000 requests per second in total. The third run is going to be 7,500 requests per second, and then 20,000 requests per second against our server. Just for you now, think about it. What do you think? Is that going to be an issue for the server? I mean, I haven't told you what the server is. It's a 4 CPU machine, 16 gigabytes of memory, fairly nice I/O. It's an M5 instance or M6 instance, pretty large. So do you think it's going to be an issue with just a vanilla Spring Boot application handling these 20,000 requests per second? We're going to see some data later on and some graphs, if it can, or if we can indeed shoot 100,000 or even more requests onto that server. All right, that's what the class does. I'll spare you all the details about that, but you can check out and clone the code later on once you leave the presentation and run it against your own projects. That will actually work. Okay, so now while these load tests are running, you can enjoy my handwriting a tiny bit more, because I told you we need to collect some data. Let me do that. Ooh, that was a straight line. We need to collect some data. I'll put them into 2 categories. The first one is I want to collect some big picture data. And you can tell I haven't been writing a lot by hand since I left school. So, big picture data. Meaning I want to get from the operating system. I want to find out, hey, how much CPU did we just use? How much memory did we just use? How much I/O maybe did we just use? And I want to know that for my server. I want to know that for my loaders. I want to know that for my probe. I want to collect that data. Just a big overall picture. Are we exceeding any limits? Are we burning through all the CPU? And then it gets more interesting, because the big picture is nice, but we want to also get, I call it the drill down. Meaning, I want to get some profiling data on the server. And this is where we're going to spend a lot amount of time looking at the profiling data at flame graphs. By the way, who has worked with flame graphs before? Okay, a fair amount of people. Who really feels comfortable with flame graphs? Right, okay. I saw, yeah, one hand, cool. Okay, so we're going to be looking at, async profiler data in a bit from the server. Then there's something else which you could collect, which I would call business logic latencies. So for example, you could count the number of SQL queries and how long they take to execute, and in general just measure how long specific portions of your code take. We're not going to have enough time to dig into that. And also a funny topic is you want to in general collect garbage collection logs. Have a look at them, how they might influence 90th, 99th percentile response times. Again, it's a huge topic, garbage collection logs, which we cannot dig into in this presentation, but this is in general the data you want to collect overall for every participant of the load test, right? And be able to analyze it, find out where we spend, CPU, memory, I/O, and then you can make an educated guess on what you should really scale. Okay, let's hope that the first test run of my test has finished. Meaning, right, here we go. What my project actually does, what this funky class, what it does is, it generates all that data using simple Linux tools on the machines. So again, you could use, if you're using AWS, you would have some dashboards and some other metrics and libraries and frameworks. This tiny class is just very simple Java code, uses some Linux tools to get the CPU data, to get the memory data, and it downloads all that data into my target results folder, which you can see here highlighted. And we have a couple of subfolders here. There's a subfolder for every test run, so with a timestamp, which you can see highlighted here. And there's also a plot folder, and I want to have a look at the plot first. Let's see what this file shows. First of all, it shows an histogram, and I know some people take offense with that and saying it's not an histogram, but actually it is a high dynamic range histogram, and we can again debate that later. What do we see here? At the moment we have one line here, a blue line, which is our 1000 requests per second test run, right? This histogram shows the response times the probe got. So again, remember the probe is this one machine. It sends requests. Hey, give me the current text numbers, and we see the response times here. On the left, you actually see these response times, the latency, in microseconds. So you have to divide them by 1000 to come up with milliseconds. So in fact, the probe got response times like 1 millisecond up until 1.4 milliseconds. Really short response times. The server didn't have to do anything. They all live in the same AWS network, so it's very short response times. Down here, the x-axis, you see the percentile, meaning you can go along this blue line here and say, hey, I don't know if you can read that up there, but there's a tiny box popping up. You can see the 50th percentile, meaning, hey, 50% of the requests took up until 1107 microseconds, or 1.1 milliseconds. And then you can go up here even more and find out the 90th percentile, right? And you see they took 1170 microseconds, and so on and so forth. The problem is these load tests only run for 30 seconds, which is we don't have enough data points actually to make that line go up till 99.9 percentile or even more. So you would have to run these load tests for a long amount of time to get all that data. The plot gets interesting because for every test run we do, the plot gets updated, and then we'll see, quite drastically, are we going to have a problem now that we have like a 10,000 requests per second test run? Are the response time is going to be any different? And it's just a good tool to have in your bag to have this HDR histogram to quickly see graphically, hey, where is the whole story going? Right, while we're waiting for the second test run, by the way, I just refreshed the page. The second line is already here, and you can see the red line here is 5,000 requests per second. Interestingly enough, it even has some smaller response times here, but you have to, and this is kind of a big topic. We're talking microseconds here, so like 10 or 20 microseconds. And actually you have to, even though now on the histogram it looks like a difference and you think, hey, 5,000 requests per second, the response times are even shorter than before, it's actually negligible, hopefully, I don't know, either of these two. Later on you'll see with the bigger response times that these two lines are actually pretty much the same. Okay, while the thing is running, let's see what data we collected. Back in my project, the first test run with 1,000 requests per second, what we have is we have subfolders for every loader. So 1, 2, 3, 4 loaders, which you can see highlighted here. A folder for the probe and a folder for the server. We're just going to quickly look at the loader and what data it contains. The loader has operating system data, a subfolder. Remember, I wanted to get the big picture. And again, this is just these Linux tools output, for example, showing a CPU log. So I'm quickly going to explain to you how to read this log. The load test run 30 seconds. We do snapshots every 10 seconds. So this is one CPU snapshot. This is another CPU snapshot. This is a third CPU snapshot, right? And you can ignore all these columns and simply have a look at the upper right corner where it says, hey, on average, all my CPUs were idle for 96% of the time. Or they were idle for 99% of the time, or they were idle for 99.77% of the time. Meaning the CPU didn't have to do any work. That's how you read these CPU snapshots. Same goes for memory. My loader had 15 gigabytes of memory. You can actually see there were even 4 snapshots being made, 1, 2, 3, 4. And the loader had to use 430 megabytes of memory to generate the load, which is fine in that case. Same goes for networking. By the way, networking is here we have 2 rows representing one snapshot with many different columns. The only columns you're interested in are essentially how many kilobytes here did I receive and how many did I transmit. And I can see this loader, received 66 kilobytes per second and transmitted 59 kilobytes per second, which is far away from the 100 Mbit or 1 gigabit the machine can actually send or receive. But the funny thing is, in my test runs, I tried to make the network adapter the bottleneck and generate so much data for the server that not the CPU or the memory was the problem, but the network actually was the problem. And a tiny story on that is that Amazon or AWS actually not only counts the bandwidth, like the 100 Mbit, but it counts the number of TCP packages every instance receives, and there's a limit. And once you hit that limit, it starts dropping these packages and you get faulty responses. And I was like, what the hell is going on? But it's just a tiny thing to keep in mind because in real life, I never saw that networking itself was the problem load-wise. But it's just, something to keep in mind once you hit these bandwidth and package problems, limitations. All right, we have that. What also helps is, and this is just, again, for us, for me as a lazy developer sometimes, when I run these load tests, I have to remind myself, hey, I need to quickly double check that the load test itself was successful. Meaning it's not just so super fast because suddenly I called the server and I got like a 400 back or internal server errors. I want to make sure that every request I sent, obviously, in this case, HTTP request, was successful. And this is just a texture representation, again, for this very specific load test, meaning in second 0 of the load test, we sent 250 requests to the server, and they all came back with a 200 status code. And I just, want to quickly visually double check, hey, every request was actually successful. There's even other data. What I personally found helpful. Please ignore the upper part here with the integral and whatever. Let's focus on the lower part, the throughput part. I personally like, seeing these visuals, throughput visuals, for example. I told this very loader, hey, you need to send 250 requests every second. And that straight line you can see here tells me, hey, the loader actually sent 250 requests per second. It didn't send just 100 or 1,000, whatever. Just having these throughput lines is actually quite nice, especially also on the server, where you can see, hey, the server consistently handled, these 1,000 requests per second. All right, enough big data. Big data is a nice word. I can skip the loaders, the other loaders, the probe. I want to have a look at what happened on the server. The server has the same data with the operating system and the CPU log. And again, for this very first test run, it had to do some work here in the first test run. It was only idle 83% of the time. The question is, what could that be actually? Why was the CPU being used? Because later on, the CPU again was pretty idle. I mean, the server didn't have to do anything almost to handle these 1,000 requests per second. Just keep that in mind for a second. What could that be? And I told you I'm going to spare you the garbage collection logs and all the other stuff. I want to dig down a bit deeper into the async profiling for a second. What happens is the server runs the async profiler and it generates a flame graph, this HTML file. And it's actually a CPU flame graph. For those of you who haven't used flame graphs before, there's different types of flame graphs. You can, track your CPU. The CPU, where was the CPU spent in my application? You can track the memory. Where exactly was memory spent in my application? And there's also something which is called wall time, where you can even find out where exactly, was I waiting for I/O requests, for example, that sort of stuff. We're only going to focus on the CPU profile for now. Just finding out exactly where did my application spend its CPU. If you have never seen a flame graph before, don't worry, I'll try and walk you through it. There's different colors here that you can see on the flame graph. Red, green, yellow, orange, a couple other ones. Green is our application code, meaning green is our Spring Boot server, our servlet, our Jetty, everything in Java that we essentially wrote. Yellow is the code that my JVM actually ran. And in this case, it's the C2 compiler, which is the just-in-time compiler. So we boot up our application, and then the JVM, compiles our just-in-time compiles our classes, and that's why we actually see, a fair amount of yellow big lines here. That is CPU spent in the just-in-time compiler. And that is, by the way, also the answer to your question why we had at the beginning relatively high CPU usage, because the just-in-time compiler was working. Red is operating system calls. So when the JVM, for example, says, hey, operating system, I need to start a thread, or I need to read in a file or something like that. That is, what the red lines are. And orange is actually CPU time being spent in the kernel. And I know as Java developers, we're not really so used in what does the kernel do. It's just, interesting that you can also see it here. Now, furthermore, the thing is, these flame graphs don't give me, CPU cycles being spent, for example. They give me a rough percentage of where was my time being spent. And if you have a look at the bottom line, this is all the CPU that was spent during my load test. And then you essentially get stack traces, right? And when you hover over these stack traces, then you can see here on the left side, you can see that we have some threads running. That is true because Jetty under the hood uses threads. And then we have the Jetty code, and the Jetty code later on calls the Spring code, and later on my code. And when you hover over these boxes, it's tiny, tiny small. Then you can see that roughly 51% of the CPU time was spent in Jetty or in my Spring application code. When you hover here over the left line, you can see that 44% of the CPU time was actually spent in my just-in-time compiler. So almost 50% of the CPU was spent just my Java code, almost 50% in the just-in-time compiler. We're not so interested in the just-in-time compiler, which means we are going to filter out this yellow block, so we can only concentrate on our green block, because I want to find out where is my text controller. Remember the code I showed you earlier, this one tiny method? I want to find out how much CPU time did it spend? And then I can, go up here and see here's still Jetty code with the package names, and Spring Framework, and then here's the dispatcher servlet, which sounds familiar to people maybe using Spring. The dispatcher servlet, takes your request and gives it to your REST controller. So I'm gonna do another filtering here actually, right? And then, you know what, forget it, I'm gonna search for it directly. I'm gonna search for text controller. And I don't know if anyone just saw something happen, which is, it's difficult to see. But there's one tiny box here on the right, which is kind of purple. Maybe you can see that. And that is the CPU time my text controller method actually spent. And when you hover over it, it means it's like 0.13% were spent CPU-wise inside my text controller method, which is obviously nothing, because the method also doesn't do anything. When you hover over the left, you can see that most time, roughly 6% of the time, were kind of spent in JSON. And JSON is the library which takes my text rate object and converts it to JSON, right? That's how you read these type of flame graphs. Now that you're experts in reading flame graphs, hopefully, we are going to make it a bit more interesting, and we're going to have a look at Spring Pet Clinic, because I did this very same experiment that I took, my for loaders, I booted up a Spring Pet Clinic application, and I hit that Spring Pet Clinic application with, I don't remember exactly with how many requests, and I just hit one endpoint. In case you don't know Spring Pet Clinic, you have this, it's a simple web application, Spring Boot. And you can find, owners of pets and veterinarians. It's such a difficult word to say. And when you click it, you just get a list of, 5 or 6 vets displayed. That's what this endpoint does. And I wanted to find out, well, first of all, how many requests per second, can I hit this endpoint with, and where exactly does my CPU time, get spent? And again, for you, maybe think about, where do you think, even without knowing, Pet Clinic, the internals, where do you think most CPU time is being spent here, rendering this one tiny HTML page? Yeah, a list of 5 vets. Where's the CPU time being spent? Well, let's find out. So let me see. I have a folder somewhere here, which hopefully says Spring Pet Clinic. First of all, let's look at the plot. Right. What does that histogram tell us? I did one test run. It only shows one test run, 2,300 requests per second. And when you look at the latencies, you can see you have to divide them 2 million by 1,000. Then you have milliseconds. And then another by 1,000, you have seconds. So actually, I hit this Spring Pet Clinic endpoint with 2,000-ish requests per second. And I suddenly start getting response times between 2 and 8 seconds, which is super slow. Which also means that the server has problems with its resources, kind of. And we definitely need to do something, increase something to scale. But the question is, what exactly was the problem by hitting, this one endpoint with just 2,000 requests? Well, let's find out. Again, same thing. I collected the data. You need to make sure that the data is kind of there for every participant. And just by looking at the operating system data CPU log, you can see at the snapshots of the CPU that the CPU was idle for 0% of the time. 0. The CPU effectively was dead. So 100% CPU time was being used just by sending these requests. And I wondered, what uses all that CPU time? Looking at the memory, you can see, the big picture is kind of, 2 gigabytes memory being used. That is not, the main issue. Network has bigger numbers than you saw before with the, receive kilobytes per second and transmitted kilobytes per second. That was also not the problem, though. I wanted to find out, where's the CPU time being used? Well, in comes our async profiler and the CPU profile. Again, a pretty similar picture, just a bit different because it was A longer test run, meaning that the yellow bars on the right are smaller because the just-in-time compiler was already had already done most of the work. And when I filter in again, I can go up here. I can search Jetty, Spring, blah blah blah, and then I can actually try and again search for my vet controller. Let's see if I can actually make it. So my vet controller, the method which gets these veterinarians out of a database, for example, or an in-memory list here, it actually only used 1% of my CPU, roughly 1.38% of my CPU. And when I look here on the left side, I wonder what is that big bar here? What uses so much CPU? And I can see here's my dispatcher servlet, which is fine, Spring. And then we immediately go into thymeleaf.view.render. And actually, once you go up the stack trace, you only see thymeleaf here being executed. Looking at it, hovering over thymeleaf.render, thymeleaf needs almost 60% of the CPU time to put the data that Spring got from that method and render this HTML list, these 5 whatever rows in the table. And that is, by the way, not a diss on thymeleaf, but it's just that thymeleaf is super CPU heavy. And our load test that we did is essentially effectively only a load test against thymeleaf and nothing else. And are you gonna swap out thymeleaf now at the end of a project for something else? Probably not, but it's just something to keep in mind, to be aware of. Which libraries or which frameworks might be CPU heavy, memory heavy, I/O heavy is a bit different, but just keep that in mind. I was actually rather surprised to find out that thymeleaf uses so much memory. Yes, please. Yes, it's only CPU time, exactly, yes. It's only CPU time. And wall clock time is actually maybe the better thing by default to have a look at, when looking at flame graphs, but it's something I didn't want to immediately go into, because just looking at CPU time at the beginning is a bit simpler to understand for these flame graphs. All right, so CPU time, thymeleaf. Let's go back and let's see if our 4 test runs have actually finished. I already almost forgot that we were working on these 4 test runs. Right, so I have 4 subfolders for my 4 test runs. Let's have a look at the plot. We're back again in our load testing scenario from before. And we have these 4 lines here, 1,000 requests per second, 5,000 requests per second, 7,500. And you can't see them anymore because they're all pretty much the same line now here at the very bottom of the histogram. We have one test run with 20,000 requests per second, where you can see suddenly, ooh, here the percentile is roughly the 40th percentile, and suddenly then 60% of the requests, they take like 100 milliseconds, 200 milliseconds, 300 milliseconds, 400 milliseconds. So they take 100 times more, 200 times more, 400 times more than before, meaning our server is definitely at its limit. And again, you can have a look at the data, the CPU data overview, see that the CPU is the problem here. But that again just gives you a quick overview of, hey, do we now have a problem? And actually, it would have been more sensible to put in even more steps, tinier steps, and then we would see that roughly at, I don't know, 15,000 requests per second, this very specific server under this very specific load for this very specific load test comes near its capacity. And then we would have to increase the CPU in this very simple case, and we could shoot even more requests per second against the server. That was a fair amount of data. A fair amount of load testing, analyzing data. I'm happy if you just take a couple of core concepts, from this stuff away. Meaning that, just go ahead, create proper load tests, make sure to collect that data, and make sure to collect these profiles, the profiling data, the async profiling data, and go and look through them and try to analyze the data properly. That would be a big takeaway here. Now, there are a couple of slides, though. Part 3 of the talk. there are some practical challenges and hints I wanted to talk about. What you saw me do is typically what we all like to do as developers. We want to always do limit testing. We want to find out, hey, when does the machine break down, kind of like, can we send 100,000 requests against the server, and then we're kind of happy to see the machine explode. Load testing really isn't about that. It's more about, finding out what is my sensible load that I encounter during the day, and even with some buffer for some, specific events, and then do load test against that, and not try to find out when is 100% CPU time being used, but when is like, am I going to be happy with 20, 30, 40% of the CPU time? That is just, consistently, that's good. Leave some buffer. Don't always, try to kill the machine with these load tests. And also, obviously, you need to use real-world scenarios against a relatively prod-like environment, which is hitting one endpoint, which is a super simplification for this talk. But sure, in even bigger scenarios, you actually need to do what you saw me do, meaning test the individual parts and pieces, microservices, test the whole, big picture, get the data for everything, analyze the data for every participant of the load test, and then try to find, which is a good intro, try to find the weakest links. Because it doesn't help if you auto scale some random servers into oblivion if they're not the problem. They can just make the problem worse, in the back end, so to speak. You need to find the weakest links and make sure. I put the database here, which is kind of mean, but often the database is a weaker link. And make sure those scale first before you think about scaling these application servers, random application servers up. And a good tip for that is, there is the flame graph you saw me create is actually just from one server, but you can create distributed flame graphs, meaning you can create them across many machines, merge them together. There's some tools for that, and then you actually see a pretty cool distributed flame graph against your whole microservice landscape for your load test. Super cool to look into, and you'll see some. I'll put in some links here in the end. A second point is expectation management. The thing is, my personal experience, when I did a lot of consulting still, when someone comes to you and asks you, hey, we could be, or says, we could be the next Amazon, likelihood is almost 100% you're not going to be the next Amazon. Especially you're not going to be it tomorrow, because a business needs to grow, and you're not just randomly going to get Amazon-like scaling problems. And you could just say, well, Marco, well, that's nice. It's just a claim. So I tried to find some numbers for that. And there's a page from Stack Exchange, which is the provider of Stack Overflow and all these other stacks exchanges. And they post their performance numbers online. And when you scroll down, you can see how many web servers they have, how many SQL servers they have, and all this data. You can have a look at that yourself later on. Just looking at the web servers, they seem to have 9 web servers. On average, roughly, let's say 300 requests per second, with a peak of 450 requests per second. I think the Stack Exchanges and Stack Overflow are among the top 100 websites in the world. And I know there are specific scenarios where it might differ, but I just want to say that if they have like hundreds of requests per second, really hundreds, like 100, 100, 100, you're not immediately going to have like 10,000, 10,000, 10,000 tomorrow, except your Alipay, one of the big Chinese ones, or Facebook, whatever. But then you're probably not sitting in this talk here by me, learning about load. And especially for small business applications, and that's where it comes back to Thymeleaf. You can be happy to have like tens of requests per second, and then Thymeleaf is not going to be the problem at the end of the day. The servers will be, unless you, what I've seen plenty of times also is create hundreds of SQL requests, for example, for one specific tiny workflow. Then you need to fix that first before thinking about scaling random servers in the cloud. Tiny story at the end is, I have a colleague who worked at bol.com, the Dutch, let's say, Amazon. And she said that, well, e-commerce, you always have, some traffic, obviously, people buy stuff, but it's, you know that traffic because you have historical data and whatever. And then there's Black Friday where, also historically traffic spikes and you can provision, your servers and for the additional load on that day. But it's also not kind of random and kind of, surprising. But what was surprising for her was the launch of the PS5. Because then people suddenly tried to, hammer the website, trying to reserve a PS5. They wrote crawlers, crawling the page, trying to, reserve a PS5. And that really, unexpectedly increased the load dramatically. And hopefully she'll do a write-up at some point explaining, what then happened and how they solved that. Performance awareness. Looking at these flame graphs, I see that as the topic of performance awareness. Just sometimes, I don't mean you have to look at the assembler output that your JVM produces, for example, but just being aware sometimes, where does, indeed, CPU, memory, I/O, there's not much more than that. How, do specific libraries, frameworks, where is time being wasted? You can always, it doesn't mean you have to always, improve your current project or swap out libraries or whatever. But as I said at the beginning, the next project will definitely benefit if you're kind of aware of, where time is being spent. And it's just a topic I like to go into a lot. Performance awareness, not just being blind completely, not never caring about how many SQL statements do I generate and how long they take, and then the database is a problem. No, just being generally aware of, where resources are being spent, and not just saying, yeah, we'll scale at the end of the day. We'll just put a number into a box, and then 10 servers will boot up, and then we won't have a problem. I've actually never seen it, work as like that. I put some further reading slides in here. You don't have to take photos. You'll get a QR code in a second, and then you'll find a link to these slides. Just if you're interested, the code is online. This one huge Java class I showed you earlier. You can check it out, clone it, run it against your own projects. Chatty Performance is this load testing framework I talked about at the beginning from the Chatty maintainers. And then there's a colleague Christoph Sluzarski. I think, say his name right. But if you want to get into the whole async profiling topic, he wrote an insanely good, it's not a blog post, it's just a huge manual, a huge guide, and you can learn a ton of stuff about him, getting into CPU, memory, and I/O profiling just by Christoph. And also myself, Marco Behler, on Twitter, on YouTube, marcobehler.com, on the JetBrains channel, creating stuff. Summary, my last words, maybe. Again, what I wanted to hammer home is just one thing. If you do some proper load testing, like you saw me do early on, if you collect the data and analyze the data, and not just say, oh, random data, yeah, we'll make the data fit our assumptions and whatever. If you do all that, wade through everything like that, then hopefully at the end of the day you don't have to worry about scaling your Java applications anymore, because you know where the bottlenecks are and what to change and what to improve. Thank you. I think we have time for some questions. Here is the QR code. Ooh, that's quite big. If you want to have a photo, it will give you the link to the slides. You can always also hit me up after the session. I'm around for a bit. And yeah. Are there any questions? Yes, please. I need to come a bit closer. Sorry for the video, so otherwise I can't hear it. No, I wasn't. No.
If we add the database in the mix, then the flame and everything you were showing, it will be appearing there. Like the database
So the question is, if we add the database to the mix in the Spring Pet Clinic example, will the database show up in the flame graph? And in the CPU flame graph, it won't, because it won't use any CPU time. But there's another type of flame graph which is called wall clock time flame graph, and this actually also shows you the calls to the database and the I/O calls, and then they will show up here. And then you'll see that, for example, we're waiting a long time. The JDBC driver is waiting for the database response and all that sort of stuff. Yes. So you'll need to dig deeper into these different types of flame graphs, actually. And the wall time flame graph is for most business applications where you use a database or use a message broker, is the default a default good option to have a look at, because it shows you all these things as well. Yes. Yes. Yes, please. Yes, it's a sampling profiler, yes. It takes, exactly, yeah. The question was for the video, again, I'm probably out of the picture, but it's a sampling profiler, yes. Yeah. Yes, please. Yes, a few words about distributed flame graphs. Actually, it's rather simple, a few words. What you need to do is, Christoph actually here, this link, he has a big, because he actually wrote a fair amount of code for the distributed flame graphs. Please have a look at that manual. He has a section and a link and everything on these flame graphs, how you do them distributedly. And please just follow the stuff, because he explains it, everything you might want to know about it. That's my short answer, essentially. Right. If there are no more questions, then thank you and enjoy the rest of the conference. Thank you.